Okay, so thank you very much. I know Greg well, so you don't need to present yourself. Could you present the three of you, please, just for me to?
I am also working in Master Institute for Biodiversity.
Okay, you were in last year.
Yeah,
Oh, okay, good. I remember.
I'm okay. I'm working as a postdoc in OpenGeoHub.
Okay,
My name is Larash. I was done my business, plantation business, so I'm yeah, I understand.
anyway, you did, what?
Yeah, for the University of Perugia. I studied here in University.
Perugia. Okay, so this is going to be easier because you can interrupt me and make this. I normally in some of these workshops, there is some time we left aside for setting up the work. But this takes time because you have to install R, you have to install Python and so on. Unless you really want to do it, I prefer to do it here in Jupyter Lab, asking you to pay attention, and then you ask your questions immediately to see. Because what I'm going to present is essentially part of the contents of an online book. So we have developed for this package sits an online book. And everything I show here is actually taken from the online book. So what is SITS? SITS is a package to deal with satellite image time series. It does satellite image time series analysis. In principle, this time series can come from one or multiple satellites. And currently, it interfaces with Sentinel-1, Sentinel-2, Landsat, MODIS. It could interface with other kinds of satellite, many products from data providers such as Digital Earth Africa, such as CHIRPS, for example. And it's natively, this is an R package, which happens to have a Python API. So I'm going to use Python in Jupyter Lab. My examples will be, I'm suppose you are more familiar with Python than with R, right? No?
More with R than Python.
More with R than Python.
But I'm not saying.
More with R than Python. And so you, Daniel.
That didn't matter. Any of who? More Python.
More Python. So I'll show some examples in Python and I'll show some examples in R. Well, how about that? Okay. So it's essentially the APIs are very similar. I'll start with Python, then I'll move to R. But essentially, this is a very, very similar APIs. Okay. Now, what is the whole issue about SITS? Well, the whole question about SITS, it's because we have a lot of analysis-ready data collections. These data collections are available on services which include the CDSC, the Copernicus Data Space Environment. It includes Microsoft Planetary Computer. It includes Digital Earth Africa. It includes Amazon. So there's lots of services who have the data. And the data is data from essentially data, which we call analysis-ready data, produced by the space agencies. Now, analysis-ready data collection includes the data comes with clouds and gaps. In order to do machine learning, that's what we want to do. We want to improve this and to produce what we call data cubes. So the essential here is to take an analysis-ready data collection and to produce a data cube. A data cube is a regular organization of space, and where if I take one layer of the cube, I get an image in time. If I take the horizontal, let's put the vertical layer, I get a time series. So a set of images put together by which I can recover a time series, or I can recover individual images. Oh, so far so good? Okay. So now, essentially, we are dealing with two kinds of data types. We have the data type of a data cube and the data type of a time series. So I'll show some examples so that we can, so I'm taking in the book, let me make the book actual size. So the book consists of a lot of chapters outlining the different types of how to build a data cube, how to operate a data cube, how to work with time series, how to do machine learning, how to do validation and accuracy, how to work with vector data cubes, and including some, for example, advanced topics like exporting data. Oh, I want to export my data to X-array. I want to export my data to stars in R. Well, here's how you do it. Okay. So the basic here, the idea is that you take a time series out, you build a data cube, you take a time series, which is a series of values in multi-dimensional because there is multiple bands. And these values are then sent to, based on samples, they are used to train a machine learning model. And then the machine learning model learns how to classify all the time series in the cube. Then the resulting map that you get, or the probabilities that you get, normally are noisy. It's common that you have, can you all see here? This is typical an output of a pixel by pixel classification. You have some noise because of the variation, borders, and so on. And then the second phase of the classification is to do what is a spatial smoothing. So after you classify all pixels, you do a spatial smoothing to clean up and to remove the outliers. This process we call space later. So SITS is a time first space later package. Okay, enough of this. Let's get some examples. Any questions? Give you some examples which are better. Okay, so I said I'm going to start with Python here. So I have a Jupyter Lab. And then I execute. This is not problem. This is something strange thing about the virtual environment. And by the way, in the book, there is a chapter who says setup, how to install R. Since this takes time, this is well described here. Okay, so go here, setup, quick tour. Okay. So here are some examples. Here are some data sets that these are points, pixels, which have been field collected and field collected associated with a class of land use class, pasture, natural vegetation, natural cerrado, natural savanna, agriculture, and so on. So here I load the data. And can you see, I don't know how big it's, can you make it full screen? That's what I wanted. here. Does it get better? Okay. I think I can even make it bigger, like this.
Yeah.
It's too big, or it's okay? Huh? Okay. So essentially here, what are these values? So this is a latitude and longitude, a start date, an end date. So this is like a time series, okay? It says it starts on date 30th of 9 of 2019. It ends on 29 of 9 of 2020, so 1 year. The label is pasture. And it also contains, it's not showing here, but it's also, no, this is what comes from the field, okay? This comes from the field and says, okay, this is what people have given to you. Dot, dot, dot. It annotates. Okay. And then just that I have to find out on the screen here. Okay. Okay, so these are 2,302 samples. Okay. Now what I'm going to do is create a data cube based on these samples. So what I'm doing the following. Copy here. Jupyter Lab. Okay. So here I have samples. And the simplest thing is to get the maximum latitude, the minimum latitude, the maximum longitude, and the minimum longitude. So this is like a region of interest out of my samples. And I define an element, a region of interest, consisting of this latitude, maximum, minimum, longitude, maximum, minimum. And here, this is an operation in sits. I am going to retrieve a data cube from a repository, the Brazil Data Cube, which already organizes things as data cubes, from a collection of data. This is the satellite is CBUS, and the band is wide field imager, so it's an imager of wide field. And this is 16 days, so every 16, this is an organized data cube already. And with bands NDVI and EVI, with the region of interest which I've selected earlier, and with the same start date and end date of my field collection. So I'm putting together a subset, real big collection, for which covers my area of interest. This is very typical. You would have an area of interest and you say, oh, you have this repository with Sentinel, with Landsat, with whatever, and I select an area here, which is my area of interest. So now I run this, and
One quick question on the, if you define something, but you don't know, or you define something that is not according to the actual data set, what happens? Do you need to know all the specifics of the thing, or does it, if I put, for example, maybe CPAS, there was no data in 2020 for some reason, or if the archive starts before, this kind of thing you need to know, no?
You need to know this kind of thing. There is something called SITS list collections, which you can run. Here it gives me all the collections that we they are available. So this says, for example, in the Amazon server, AWS, there is Sentinel-2A, the two Sentinel-2As, and there is Landsat. Okay? But the Landsat in AWS is not open data. These ones are open data. The Brazil Data Cube, there is CBIS, such as Landsat, the MODIS, Sentinel. In Copernicus, there is Sentinel-2 currently and Sentinel-1. Digital Cube Chile, Sentinel-2. In Africa, there is this ALOS Pulsar Mosaic. There you go. There's the DEM. There's the European Commission DEM. Landsat. So here's what rainfall. Essentially, if a provider, we contact the providers. For example, we ask Digital Earth Africa, what are the data sets that you like to make available? And we say, okay, give me the endpoints for this, and this is what you have available. There's NASA HLS, there's Microsoft Planetary Computing. So there's a lot of, let's say, data, Terrascope with world cover from ESA. There's a lot of data sets, and they have a period where it's global, unless. But it's a good point, Greg, because it can be improved, certainly. Now, we did that. And what we're going to do at this point, this data set is a data set which, when we created this, selected this ROI, we area on the server. It's not on our computer for the moment. It's set, it's on the server. And here, whoops, did I copy? No, I'm copying the DR. I need to copy. The DR in the Python, you can see the codes are absolutely similar. The only thing is that in R, you have this arrow. In Python, you have the equal. Otherwise, there is no much difference. Let's see, Python. See, Python temp GFPy, and that's temp GFPy. So this, okay, it plotted the first NDVI. When I say plotted, you plot something. Essentially, if you can set up so it plots red, green, blue. If you don't say anything, it will try to get the most reasonable plot you can get. In this case, it's the first NDVI with this palette, red, green, and yellow. And this is the values assigned from 0.2 to 0.1 from this region. So nice agricultural region with some natural cerrado and some pastures, and so on. So this is basically, I'm plotting the cube. So now I have a data cube, and I can even type the description here. So what is this? Well, this is a SITS data cube, a source Brazil data cube collection, blah, 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 sensor, tile, this characteristics. It's basically telling you what are the characteristics of that data cube, where it starts, where it ends, which projection it is, and so on and so forth. Nothing too fancy. Okay. Here it says essentially the fact that this highlights the fact that this data cube is essentially a metadata. So it contains what we call file info, which is the information about the actual data sets, the actual pixels, which are in files, which you have copied to a directory. Here, I have copied this to a directory, so there's some TIFF files there, and I recorded the stiff files and the extent of the stiff files in this object called LEM cube. So when I say LEM cube file info, I say where this is the data sets, the actual images which are indexed by this object. So this description here, it's a table, it's an array or a simple relational array that contains the description of the stiff files. Okay? So now I have a data cube consisting of a description, a lot of files. And remember, I started all of this with a set of samples collected in the field. So I have samples collected in the field, I have a data cube, but I don't have the time series yet because I need to link the location of the samples to the files in the data cube. This is the next thing we do. Oh, we can also, for example, ask the timelines. For example, what's the timeline of this cube? If you want to know how many time instances does it have? So here's 23 instances. It sets the dates here, the 16th of 10, starts on September and ends in 30 September, ends in 29 September. Okay, so I have the instances, and now I am going to get from those samples that someone gave me from the field and the data cube, I'm going to obtain a set of samples. So here, oh, it's the R version. Come on. Of course. I should have picked the, I should have picked, yeah. Thank you very much. You could put equal for R2 in principle. Okay, so it collected the time series here. And let me show the time series. Yes, copied, lab, run. Okay, so now we have a time series for 1 pixel. This time series says what? In 30th of 9 of 2019, the EVI was 0.201, the NDVI was 0.4, and so on and so forth. And then in 9 of June of 2020, there was 0.37, the other one was 0.525, and so on. So this is, I now have lots of time series. Finally, I got the 2 elements. I have the time series from the samples, which you pick up this, it's like a barbecue or churrasco, as we say in Portuguese. You just put a slice through the meat, the data bit, the data cubes, and you obtain the values. Okay, and then you can say, out of those, what is the summary of this? In other words, how many labels do I have of each class? So here we have 136 of Cerrado, 1,250 of agriculture of 1 cycle, 790 for cropland of 2 cycles, and 123 for pasture. More or less unbalanced data set, but that will do for the, oh no, in this case, I decided that I don't want to have too much imbalancing. So I'm going to say I'm going to reduce this imbalance. So I don't like this. So I have a function called reduce imbalance, which says, okay, I want to have a balanced data set with a minimum of 150 samples per class and a maximum of 300 per class. And if I do the summary again, you see that I have improved the imbalance. So now I have 150 for Cerrado, 312 for scrubland, 316 for 2 cycles, and 150 for pasture. So this is a very typical situation where I may decide or not to use imbalance or balance samples. Is it clear? This, or I'm sure you have met with times when you had the imbalance samples that you had to balance them. So this is a way, this is one thing which is available here. Okay. And we can, for example, take one band and one label, and show this. I can show everything, but for simplicity's sake, I'm going to do the following. I'm going to select from all these samples, all of those that have associated with the label cropland 2 cycles. And then I'm going to select all of those who was associated with NDVI. And then I'm going to plot all of samples of that class, crops 2 cycles with NDVI. I could do, if I say plot everything, it will plot. Now, just because it will take some time, we're just plotting one. Okay, so what we have here? We have here, how many samples here? 316. So each blue line is one of 316 lines. The dark brown line is the median. So if I take the median of the 312 in time 1, time 2, time 3, this is what I get. In the yellowish, sort of yellowish lines, you might see here, may not be so clear. These are the first interquartile distance and the third interquartile distance. Now, what you can see that there is a pattern. The pattern of 2 cycles of cropland in NDVI. Why do we have 2 cycles of cropland in NDVI? Because you have soil, barren soil, and then you plant something, and then the crop grows, NDVI increases, then you cut the crop, NDVI decreases, and then you prepare the land again, and then you sow something, and the crop increases, and then the NDVI increases, and then it cuts. The other thing you can see is that the NDVIs, maximum NDVIs, for the 2 crops are not the same. First crop has a higher NDVI than the second crop. Why do you think that is? It's a different crop, but there's also one reason. The region, the kind of region, the precipitation crops is much better in late. This is late, so we're talking about late one year, early next year. So it's October, November. It rains normally. It rains in October, November. It sort of waters the land, and then there's enough water for the first crop to grow, which is soybeans, and then the second crop is normally corn. In good areas where there is enough of water in the soil, this NDVI for crop will grow higher. It grows slower because this area does not have too much, or does have the optimum quantity of water that would be needed to get the full productivity of maize, of corn. But even so, it gets the corn, and you sell the corn, and you're happy. So it's the fact that you're not dealing with optimal circumstances, but you can see here. So you have the two crops. So
The images are not too good, right?
that's a very good point.
Before the crop rise, yeah, that one. There's clouds that are not well masked or something like this.
Yes, you can see that here in the end of the year, and in some places, there are clouds. What happens here is that the software takes the time series, and when it finds a cloud, it does a linear interpolation. So imagine there is a pixel with no cloud, and pixel with no cloud. So it linearly interpolates here to try to create a linear interpolation. There are different options for interpolation. This is a very good research topic of selecting interpolation. What is the best interpolation when you want to remove clouds? And what are the best techniques to remove clouds? Linear interpolation is the cheapest. Okay. We use linear interpolation. It works mostly. But of course, one could improve a lot in terms of which interpolation. But there is noise, a lot of noise related to clouds. Now, the other thing, now that we have the time series, now that we have the data cube, the next thing is to train a model. And to train a model in SITS is relatively simple. Okay, that's a good point. Very good point. Okay. Imagine that you have here a set of images, okay? And these sets of images come as they may. The satellite, because when you have, for example, let me give you one example here. Okay, this is the next thing I'll show, but okay. When you go to Copernicus data space infrastructure, okay, ecosystem, and you ask for a tile of Sentinel-2, and you just say, I just want a tile, you may get something like this. Because the satellite passes in an inclined orbit towards the Earth, but the cuts of the system, the tiling system, are regular in terms of at the equator. They may compress a little bit behind the poles, but they're supposed to be regular. So it's not uncommon that I have a situation such as this one, and that I may have, I don't have examples here, but I may have clouds. So then your decision is to decide and say, okay, what do I have here? How many Sentinel images I have, let's say, per 10 days or per 1 month? Normally, they're about 3 to 5, depending on where you live, you have more. Images per week, every 15 days, for example, there's about 5 or 6, depending on 3 to 6, depending on UFO. So you may want to say, I'm going to set up a period, and you decide based on your experience. What we normally for Sentinel, we use 16 days. For Landsat, we use 1 month or 2 months. But that's problem driven. In this case, I'm using 16 days to join images from all images inside a 16-day period. They are joined to get a single image. And here, what you try to get is the best image which has less clouds and which matches everything, which covers the whole area. We call this a regularization of a cube. Those of you who work with Google Earth Engine know there is something called the median. You ask for an entire year of Google, is Landsat in Google, and you ask for the median image. So it takes simply the median value, take the clouds out, take the median value, and you get one image per year. That's the median value. Here we want to preserve the temporal information. Therefore, you don't compress so much. You compress a little bit by 16 days or per 1 month, so that you can still keep a reasonable temporal variation. And then you can, for example, this example which I was showing, this is a 16-day. So you can see if I had, of course, 1 year, a single date, I will never see the temporal variation here, right? Because if I take 1 date or take 4 dates, the temporal variation would not appear so nicely. It's a compromise. You want to get the temporal variation, you want to get the noise out. Okay, so it's a very important point made. Now, so, like I said, once you have the time series, once you have the cube, you have the samples, very nice. Now it's time to train a machine learning model. So what is training a machine learning model? Training a machine learning model should be simple. At least we believe should be simple. Because in the end, conceptually training a machine learning model consists of 2 kinds of objects. One is the algorithm you want. The other one is the data set, the training data. So at its most simplistic, for less experienced users, you run a machine learning model by saying, my samples are the samples I collected earlier, a time series, and my methods, it sits random forest. And in many cases, this is not, for example, you can exchange here if you want to do support vector machines, or for example, a deep learning method called temporal convolution neural networks. So, or you may want a light attention model, light TAE. Or you may want a NextGBoost model. Or a light boost, a light boost algorithm. So all the points here at each point, we are trying to make the user happy by saying, how do I train my model? You have an algorithm, and the idea is that there are default parameters for each algorithm, which of course you can set up if you want to go into detail. But there are defaults which help your... Beatriz, is it possible to get a glass of water?
Sure.
You want to get... You want to get a trained model as simply as possible. And then I can plot this model. So this is a machine learning model. Plotting it is interesting because the plot shows how these models operate in the case of a random forest. Imagine that the random forest model does not have anything spatial in it. The random forest model is a pure, input-driven, parameter-driven. So when I have two bands, NDVI and EVI, and I have 23 samples per band, random forest simply considers, no, sorry, it's not so easy to see. This is what I wanted to show. This small bit here, which let's see if I can.
And one being the first time step of
NDVI 1 being the first time step NDVI. EVI 12 being the 12th time step of the NDVI. NDVI 12, the 12th time step. So what I'm doing here is the following. I'm using values in the time series. So the first NDVI here is what the model is seeing. I'm using this because this is informative to separate the classes. This is, in the end, it's the, in a certain sense, the information content, the separability content of each parameter, and the parameter here being the combination of band and time. It's not smart for time, but it says, okay, some combinations of band and time are more important than others. For example, NDVI, EVI 12 or NDVI 12 has to do with the fact that if I walk 12, I'm here, more or less. This value, which suddenly is high here and low here, is an indicator of the presence of something or the absence of something. So normally it is in situations where you have breaks, the NDVI tends to concentrate on the peaks and the breaks, where it can separate this kind of response to response from other length types. So we have found, if you, for example, would use a deep learning algorithm, your result would be very different in terms of, because it would use not necessarily the way the random forest does, it would try to operate in relations between, for example, an attention classifier would operate in relations between groups of samples. Normally it says, oh, I have my attention head here in the mid of the year, I have an attention head here. I will concentrate my attention on the informative bits of the code. But let's just continue here. So.
Can I ask you a question?
What?
Well, your thought random forest there, is it doing, like, because you don't give it any other, is it doing the standard cross-validation by itself? You tune these things. I mean, I guess it's made so that the user doesn't need to think about it. But behind the code, I guess it's basically using 100, the very standard random forest. It takes 100 trees, and then of course out of each tree it selects some of the. Not all the parameters are going to one tree and does the cross-validation, and then considering what the result of each tree is, gives a probability. So the probability that comes out of the random forest is a probability associated with the output of 100 trees. So if you have the 100 trees say pasture. But does it split your data, your sample data that you gave it 150 or something? I mean,
it actually splits per class. so that in each tree, I'm not going to have for each tree all of the samples. This is to minimize bias, yes.
More than like you did from your possible.
Yes, so here, so if I now go, good question. If I now go here to the algorithms, you have a sample of the algorithms available. So the interface for each algorithm is this seed strain. And through the seed strain, you can run the random forest, which we're showing. And this is one example. You can run the support vector machine. You can run the extreme gradient boosting. So here, all of them is seed strain, samples, method XGBoost. You have a lot of parameters in XGBoost, okay? And you can set these parameters if you want. They're available. We're just saying if you don't want to do it, we have a default for you. The multi-layer perceptron, the traditional neural net. So these are the default parameters for three deep layers and the dropout rates and epochs and so on. There is the temporal convolution neural network, which is very much used. A lot of people use it for satellite image time series. So again, it has, these are the defaults, the parameters, and residual 1D networks, ResNet. This is from Microsoft, the traditional ResNet from Microsoft adapted to 1D. Some attention-based models, which are being published by a Frenchman called Garneau. So these are methods which work well and so on.
And also graph.
Huh?
Is there also the graph neural network?
No, not yet. Not yet. We need to be mindful of many things. Now, let's suppose you want to go one step down and you say, I'm not satisfied with the defaults that you're giving me. So what do you do? Okay, no problem. We give you the satellite image time series. We give you functions for model tuning. So the tuning is where you go into details to say, I want really an appropriate set of hyperparameters. I want to set the learning rate. I want to set, because these kind of hyperparameters, they are very, of course, they depend a lot on the learning rate, how fast it converge. I have a nice example here. Sensing. Sensing GitHub. Let's see. That's a nice example that for those who want. I think I have a torch shop. I had implemented some optimizers. Torch shop. Okay. So this is an example of an optimizer. Can you see the... So this is a very simplistic example of an optimizer. And of course, optimizers start from one place and try to do the gradient descent. And they may get at different points because of different rates. You can see the first optimizer converge to this, which is a local optimum, but not the global optimum, which is this one. And again, you say, well, what is based on testing all of them? What's the best learning rate? What's the best kind of many parameters that you sent up. So this is tuning. If you want to, we use what the famous guy Bengio, who won the the Turing Award. Essentially, this is randomly chosen trials. So tuning, Bengio has a classical paper who says using randomly chosen trials is as good as running a full trial, which would be too expensive. Okay, so where are we? We were here. Now, okay, so we did the random forest classifier. And then we are about to do the data cube classification. Okay. So we have a random forest model, and then we have a random forest model, we have a data cube, and then you do a classification. You say sits classify, give me my data, my model, and some parameters. Here, these parameters are optimizer parameters. How many cores does your machine have? How many size does your machine have? What's the memory size? So, or what is the size of the GPU if you're having a GPU? And then you plot the result. The result here of the classifier is not a map. The result of the classifier is a set of probability matrix. So each classifier gives you a number of probability matrix for each class. So if you have 4 classes, you're going to have 4 probability matrices. In this case, for the label cropland 2 cycles, I have 1 probability map from 0 to 1, which means the classifier assigned the probability of 0 to 1 of this pixel being a cropland with 2 cycles. And the same will go for all the other classes. Okay?
This is then a static probability. Because let's say you're using time series to generate this probability.
No, we're not using, no, we're using the time series to model the random forest, the classification, the time series are the input for a machine learning model.
Yes.
So the machine learning model will now pick each pixel, which is a time series, and assign to this time series, which is this, you see here, remember, I have for each pixel, I have a time series. Okay, what is the class that I assign to this time series? It can be pasture, agriculture, water. So it will say, I assign for class water, my classifier gives a probability of 0.1. For class agriculture, it gives a probability for 0.8.
Yeah, that's actually my question. So can you somehow also reduce like time series its probabilities? Let's say if you want to see this pixel in 2019 but also in 2020, can you do it in one month or you need to run separate years?
You need to run a separate years because of the way the classifiers operate. This is a very good point. If you had a classifier, these kinds of classifiers, they assign probabilities to classes. When you put them in classify, if you put them in regression mode, this is another story. When you put them in classification mode, they assign, the output is a probability of the class existing. That's the way these classifiers operate. So if you want to say, well, what's the probability of pasture in 2020 and forest in 2021? You need to classify 2020 and then 2021. Because of the way the classifiers are organized. So here you have for a given year or for a given period, what the classifier is telling you that it found. But since the classifier gave you a probability, that was my earlier point, since the classifier gave you a probability, okay, now I can do something important. I can do a spatial smoothing. I told you that what we have, when you work with pixels, you don't consider the spatial neighborhood. So we need now, after we get the pixel classifiers, the time first, it's very useful to get the rest, the neighborhood effect. So for this, we do a spatial smoothing. So we then compare the probabilities of the pixels with the neighborhood to filter out outliers, badly classified pixels, cloud effects clouds which were not collected by the satellite algorithm, many effects that you have there. So it's always good to do the smoothing. So when I do the smoothing, here I do a smoothing. Oh, again, I made a mistake. So this is the result of the smoothing that can be compared with the earlier. If you see the maps that result, you see a lot of the outliers will be removed. There's more spatial continuity. There's a much more spatial continuity. There's many outliers here which were showing small bits and that were wiped out. And when you join now all the probability, smoothed probability matrix, you will get a much nicer map. A map that corresponds more to the actual map that we expected to see. So this is the final map. So the final map has areas of cerrado, of pasture, of cropland, 1 cycle, and cropland 2 cycles. And they are consistent, at least the croplands are consistent. They mix 1 cycle with 2 cycles. Okay, so to sum up this whole story, you have a logic which is like this. See if I can make it bigger. Yes. So the logic is you have access. Normally you have access to some collections, to Copernicus data space environment. You have access to ground truth, which you either collect visually or interpret images or go to the field and so on. That's what you have. But then you can build, based on your selection, you build a data cube, a regular data cube, which you work. And this is where you're going to apply your machine learning algorithms. And if you have the locations of your samples, you will get the type, what we call get data, and build what we call the training samples. Now, given the training samples and an algorithm of your choice, you will build a classification model using what I call SITS-train. That's what I showed you earlier. Now, if I now have a model and a cube, I can classify the cube. And I classify the cube, obtaining a probability cube, which I can then smooth and use the spatial effect, and then do a classification, final classification. So you have a step-by-step from the very basic, which is some samples in the field, and some collection, which is somewhere on the internet. And by combining them, you get a classified map in a step-by-step basis using different algorithms, traditional algorithms, random forest, state-of-the-art, attention models, and so on. Any questions? Yeah, go ahead. Yes, please. Yeah.
Okay. Two questions. So the first one, that the fifth page is being focused on satellite images. Are there plans to perhaps incorporate climate products?
We can incorporate climate products, especially we have some climate products. For example, the CHIRPS method. What if you're talking about reanalysis? The reanalysis is more complicated because the reanalysis is a 3D plus time, right? And normally we're dealing with satellite data or two-dimensional data. So we have thought about it. We have not decided if we can do it, because here everything is organized in a satellite basis in which each time you have a satellite basis. To change this would be completely different. I would advise you, if you want to use at least what I know works relatively well, is the climate data store at ECMWF. Maybe you already used it, which is really optimized for things like reanalysis. That said, if you have two-dimensional data sets, for example, like I said, where is it? Sorry. This is really data collection. For example, for Distorted Africa, okay, for example, what we have NDVI anomalies, rainfall information, the CHIRPS, climate hazard group for precipitation, monthly and daily. So normally, let's see in Digital Earth Australia, what do I have? No, I don't have so many. It's much more water, intertidal. But in principle, if you have a product which is two-dimensional, for example, mean surface temperature of daily mean surface temperature, or monthly mean surface temperature, of monthly mean sea level pressure, you can use that with SITS to classify.
You don't have it in your catalog.
I don't have it in my catalog because I'm not sure who is producing it. If you can tell me who is producing it in the stack, I'll be so happy to put it.
I mean, so for IP land, for example, the analysis, this should be on land. Think those would be fit in this category because you're not doing all the layers of the atmosphere, for instance. No?
And
that's
where are they, Greg?
land is in the climate data store.
On the climate, but does the climate data store have a stack?
I was wondering. Yes, and well, I mean, I wonder. Yeah, but let's say.
No, the problem. No, that's not a problem. And thesis,
The point is that I mean, ERA 5 land, for instance, is something specific more for the land that, and even ERA 5 in general, they have all the levels at the surface as well. And so you could treat them, I mean, the 3D part can be turned. I mean, it doesn't break the model, I think, for you.
yeah, that's what.
Someone who does atmospheric transport would not use it, but they wouldn't use this sit pattern, for example.
Okay, so I have how to build this.
But I don't know if they have the proper set. I would imagine that they do. But
I am sure at this point.
I don't know. Yeah.
No, because the I'm trying to build a stack catalog based on some variables. Download the okay.
But cool.
No, but if you really want to use it, you can put either send me a note remembering this, or put or one other thing that you may want is now back to.
And that was also part of the question. Is there a date for what is the roadmap of the development of the package, or
Yes,
just the priority?
of course, it is the GitHub from sits. Okay, so what happens at GitHub from sits? We essentially share with the users not only the code, but for example, the issues. So here, for example, this guy opened 3 hours ago, 18 hours ago, saying, can you do seed smooth for regression tests? So here, for example, are all things that some people, we make it smaller. Oh. Okay, here is where normally there are how many? Open 223 open issues and 721 closed issues, things that we've resolved. And these include not our plans, no, things that we want to do, we put here. For example, develop package to implement post-processing rules. This is something we want to do because we do this a lot. And then Gilberto Camara opened this and said, this is my plan. We want to have it. But someone says, implement random forest backwards feature selection via MDA for SIDS models. So you can, and then we say, we can do it, we cannot do it, we are working on it, and or it's a bug, we corrected it. There are lots of include SIDS SL1 LC products. So this is try to be very responsive. As you see, the number of closed issues is far greater than the number of open issues. But we would be willing to do, yes, Greg.
So I have a couple of other questions like that. Like, would you, I mean, if someone wants to use link it to their own data. So I mean,
Right.
to bring something on, I guess you can do the same thing, and instead of calling Amazon or whatever, you could call your own graph.
Yes, yes.
I imagine.
But
Yeah.
go ahead.
Well, so that's I imagine.
Yeah.
Then, is there a way to do that also with SAR data?
With ZAR.
Yeah.
Well, not at the moment, but we could do it. I mean, we've
So we should put a request in.
you should put a request because the issue here is there is a chapter, because this was just a sort of a saying how it works. But if you look here in the chapters, there is a chapter called Data Cubes from Local Files. Okay? And here we say what are the current support for planet data, for example. Because normally planet data is not available in the, but we have support for planet data. We have support for planet data. If we go to the Jupyter Lab, SIDS list collections source equals planet. Okay, so internally we have implemented the support for, so planet data normally comes at the user has bought the image or got from someone and puts his local machine. But we still need to know how many bits, what's the gain on each band, how many bits per pixel, what is resolution, what is the minimum level. We have to store this kind of data set. So essentially, we could do the same for Era 5 data or anything. If you don't,
Have to come, also do the proper homework of putting the number of bands, number of things.
yeah, I mean, if you tell me we configure the system, so we do it once and you don't have to do it every time. So you say, okay, this is Era 5. So Era 5 data, and then you refer to it as Era 5, and you say this kind of product from Era 5 is this, and then you get all of that. What's the minimum resolution, maximum number of bits, and everything, including formats. There's no, in principle, no major problem with why don't you use ZAR? I mean, this is like obviously that if the data is in ZAR, why shouldn't we use ZAR? It's just a question of people asking. It has been at a certain point, you have to be responsive to your users. And the more they ask you questions, the more you need to be responsive to them and incentivize them to ask more questions.
And in the same vein, I mean, because now in our institute, for example, a lot of people, because they were quite innovative with SAR also in the beginning, but also because many switched to Python also, or virtual.
I mean,
Python, everyone is doing XRA, an XRA.
but moving things from Python to R is always difficult.
Yeah.
But remember, here, like I said, the example I'm doing, I did everything in Python.
Yeah.
No, exactly. Yeah.
But so irrespective of the language, if people from Python are typically using XArray, what do we tell them about SIDS that maybe has an advantage or not? I mean, how does it differentiate with XArray?
Well,
a lot of this would be nice because this is really made with this satellite background, right? And so a lot of these things are facilitated, and it seems that documentation is good.
well, here,
Yeah.
I have an example. Here I have an example. Okay, I'm going to put it here. Okay, so there's a package called PySits, okay? And then you import sits as XArray. So here, suppose you have a data cube, because sits is sort of has lots of things for creating data cubes and creating this kind of things and getting data from stack and organizing, testing them. Okay, so it reads a raster package from sits. Okay, this is sits data cube. Then I say sits as XArray. So I get an XArray data set. And then I can work normally.
Yeah. Okay. It's possible to do it the other way around.
Yeah, that's
Not yet, but we do it one thing at a time. One thing that we do, now it works, is if you build a data cube, for example, if you use the facilities from sets, for example, if you want to not to have to develop your own host stack catalog in Python. Oh, I download the data cube from CDSC or download the data cube, and then I want to save it as an XArray. And then you say, okay, fair enough. I give me an XArray for that cube.
go to SIDS to get your things in.
Yeah.
Yeah, no, but for me, what we always struggle is when I want to share data with our users. If I use XRA, I would save it as R. But then I give the files to an R user, and it's always an issue on.
No, but again, we given that we have a request, we're very happy to support you. because if you have
But I remember that this is the beginning of this project. I told to Edzer, now that we're in this project, perhaps we could solve this issue of getting SAR easily in our community. And he says, oh, great, we'll do it. Like, oh, take care, like that. And he solved it in his development world, in his configuration, and it worked. And then people could just not use it because, I don't know, he has one version of SF or whatever. He went through GL or whatever. It just made it a bit complicated. Now, I don't know how it is actually because I'm not using it. But still, there's something there that makes it that it's not as smooth as things go with XRA and XCube. And in XCube and XRA is actually quite seamlessly to, people don't need to think about this anymore.
no,
It would be great to see that integrated. So
right.
we could tell people, use it, it will deal with it. But we'll try to do
No, because we would be very interested in. We also think there are many things that people working and they work in Python seamlessly, like the X-array. So you need to interface to X-array and then from X-array interface back. So this is the kind of things that but we need to motivate us. We need people who, like you, who have a team and have demands. For example, I want the ERA 5 land. I want to work with the ERA 5 land product. I want to work with ZAR products. I want to work with this. That would be very good. I think that's time. Well, thank you for being such a nice audience. It's been nice. No, it's good that that you were here, and a lot of good questions came, and I've learned a lot from the demands of this kind of, climatological, meteorological. I'm sure that we can do a lot of it. Thank you very much.
It will be a yeah.
Now.
Thank you.